This is the 8th video in a sequence of lectures on single agent search. And this is the first video that's really getting into some of the new and novel things that have been done in the last few years that really expand our understanding of heuristic search and that are correcting some of the behaviors that have existed in previous algorithms. And so this is an important step because I think this is one way that we're going to have of increasing the applicability of these algorithms to the types of problems that we might be seeing in the future. Especially as we get into things like machine learning and maybe much more complicated models of our domains where things don't necessarily work as cleanly as they have in the types of domains we've seen in the past. And so, as I said, today we're going to be looking at budgeted tree search. Budgeted tree search, or BTS, is an instance of IBEX, which is iterative budgeted exponential search. And IBEX is an algorithm that is a general approach for handling what I would call an issue of re-expansions in a number of different problems. And so we're going to look at the two instances, the two known or the two published instances of budgeted tree search in this class. And so we'll look at budgeted tree search now, and then budgeted graph search we'll come back to in a few more lectures. Okay. And so there's a paper that we wrote on a guide to budgeted tree search, which has there's quite a lot of detail in there with a number of examples that are run through and some other things like that that you can use to try and understand the algorithm. And then there's IBEX, a paper on IBEX, which is a high-level overview of the whole approach with a lot of maybe low-level details in there that some of those are removed in the guide paper. So I would recommend looking at the guide first and then going back to the original paper and looking at more of the broader details there. But this algorithm is designed to handle the worst case of IDA star, and there's a number of designs in here that are designed to make this performance, that make the overheads be very low. So practically speaking, budgeted tree search is a drop-in replacement for IDA star. If IDA star is working the way that it should, then budgeted tree search will generally work exactly as IDA star, will have exactly the same performance. But if IDA star is in the realm of having poor performance, then budgeted tree search is going to avoid that worst case behavior. And so in particular, what we see is IDA star worst case is b to the 2d. And we're going to be able to take this with BTS. And what we're going to see is we're going to introduce an overhead. So it's going to be b to the d with an overhead of log of c star, where c star is the solution cost. Okay. And what we're going to see with budgeted tree search is basically we can think about what goes on in IDA star. And we can think about how we could build, we're going to divide up the algorithm sort of into an oracle that's going to answer some questions for us. And when we're able to answer those questions, it's going to make the search be very efficient. But just as we get started here, let's go back and look at what goes on. So we'll look at some slides and animations here just to make these things clear. And so this is an example. We showed the same example. So this is coming from a 2x3 sliding tile puzzle. And this is an example of a tree when we're running with these the normal assumptions on cost, unit edge costs, and everything works out really nicely. And what we see here is we have f cost 11, there's two nodes at the top, and we have a big range of nodes with f cost 13, and then we have another big nodes of f cost 15. And what we see, we went from 2 to 16 states, so that grew by a factor of 8, and then from 16 to 79 basically grows by a factor of 5. So in this problem, this state space is essentially growing exponential. If we look at the worst case, then we could imagine that instead of getting b to the d as we grew the regular way, we could imagine getting 1 plus 2 plus 3 all the way up to b to the d, which would be b to the 2d. And what we're going to do is we're going to take the sliding tile puzzle, and we're just going to say that moving different tiles has different costs. So tile t costs t plus 2 over t plus 1. So you could imagine a tile as like its weight or something like this. And so there's different weights on the tiles, and so that's how it's going to affect the way the tiles that we want to move. And so just to give an example here, if we try and run this, this is the same example we gave in an earlier video where we saw that this tree is growing very, very slowly, and IDA star has very, very poor performance. And just to show exactly what's going on here, what we can do is we can ask what are the F costs in the tree, in the same way we looked at how many nodes there were with each F cost. So we see here the F costs go 11, 11.25, 13.45, 13.5, 13.62, but basically every node in this tree, or almost every node, has a unique F cost. And when every node is a unique F cost, then we're getting exactly the worst case performance. So it doesn't take a very small change in our domain to suddenly see that we go from something that's working basically the best case to basically the worst case here. And so the main issue here is that the nodes are not growing exponentially. And so let's go back and look at what we can do about this problem. Okay, so what we want to have happen, and we know in general that if we have a tree, okay, we have a tree that's growing, if the nodes in the tree are growing exponentially, then the early iterations are basically won't add up to something that is significantly greater than the last iteration that we do. And so there's a number of ways that you could say you can try and do this search, but essentially what we want to have happen is that I have some given F cost. So let's say I'm searching with F cost is equal to 10, and I do 100 node expansions. What I want to have happen, so let's just say I want, this is my target, is going to be B is equal to 3, let's just say. So what I'd like to be able to do is just say, well, I did 100 nodes on the last iteration. What I'd like is in the next iteration, I'd like to do 300 nodes, because that's going to guarantee that, that my tree is growing exponentially. And so what I'd like essentially is to have an oracle, which is going to tell me, if you want to do 300 node expansions, you need to use an F of 11.7. So this is the problem here, is that I don't know. I know how many nodes I want to do. If I did 100 in the last iteration, I want to do around 300 in this iteration. But what I don't know is what F cost I should use to get that number of node expansions. Okay, so in general, we just increase the F cost to the smallest amount, and we would hope that we get that. But we won't necessarily do that. And so you could imagine here, okay, I do 100, then I get 300. If I do 300, then the next iteration, I'd want to do 900 nodes. And then again, I don't know what the F cost is. So you can imagine I'd like an oracle to be able to tell me, to do 900 nodes, you'd like an F cost of 15.13. Okay, and it might say, yes, well, if you used 15.15, maybe you do 1,000,000 node expansions, and that would be inappropriate. But I want, and maybe if I did 15.11, that I'd only do 301 node expansions. Right? So the idea is that I'd like an oracle basically to say, hey, you did 300 in the last iteration. I want to do exactly 900 in this next iteration, or we'll actually be a little bit more less precise than that in the actual search. But what I don't know is I don't know how to get from the number of node expansions I want to the F cost that's going to cause me to do that number of node expansions. So you could imagine if I just had an oracle that would tell me the next F cost, that I would just say, okay, I get my initial F cost, I do the search, it tells me how many nodes I do. I would go to the oracle, and the oracle would say, this is the next F cost that you should use. If you use this next F cost, then the nodes will grow exactly by some target branching factor that you have here. And so go ahead and just search for that next value. And we could do that repeatedly. And wherever the goal is, so you could imagine maybe the goal, if the goal F cost is somewhere between 11.7 and 15.13, it would be fine in doing this iteration at 15.13, we would find the goal. We would do no more than sort of B times the previous iteration. So when we find the goal, we're going to do about a number of nodes. And overall, since this grows by B at each step, we're going to do B to the D nodes. Okay, so our life would be really, really easy if we could just have an oracle that would tell us what cost to search at next. Okay, and so what we're going to look at here is how we can build this oracle. Okay, I don't really, I'm never going to get an oracle, but I actually can just algorithmically build a procedure that's going to do this for us. And the oracle is going to come from an algorithm called exponential search. So this is an algorithm by Yao from, I don't know, 30, 40 years ago. And the idea here is, imagine that I have an unbounded sorted array. Okay, so let's look at exponential search. Okay, exponential search is designed for a problem where I have an unboundedly large array that sort of goes forever, but the numbers are sorted. And the idea is there is some entry here that I'm trying to find. This is my goal entry that I'm trying to find in the array. And I'd like to find that entry by querying the value. So for instance, I want to find a value of, I don't know, just some number. It could be 127.625. Whatever it happens to be, I'm trying to find that value. But I have no idea, like, what is the range of values that could be here, right? So these values could be, I could have, all my values could be between 0 and 1 for quite a long time. I could have millions of values between 0 and 1. Or maybe my values actually start at 100 and then go up by 1. And so this entry could be very far in the future in the array, or it could be very low in the array. But what does exponential search do? So the idea is we want to use a logarithmic amount of time to be able to find the entry here. And so the idea here is we're going to do two steps. One is we're going to have an exponentially growing step size. So we're going to look at entry number 1, and we're going to make a query. And the query we make is we want to know if we're too high, too low, or we found the value we want. Okay, and so a binary search in general is making these sort of things. Like a binary search, it takes an interval, or like if you think about a quick sort or something like that, what you're asking is I give you a value, you tell me if it's above or below what I want. So the same idea here. So I'm looking for a value, whatever it is, 127.625. I look at the first entry and I say, is it too high or too low? And as long as the value I have is too low, what I'm going to do is I'm going to grow this range exponentially. So step 1, then I'll step 2, then I'm going to step 4, I'm going to step 8, and then I'm going to step 16. And all of these are going to say too low. Low, too low, too low. And then up here, we're going to say too high. Okay. And then now I have a low range and a high range. And again, I have a comparator. My query is asking the question. It's going to be able to answer this question. Am I too high, too low, or did I find the value that I looked for? And then I'm basically going to get a binary search inside here until I find the value that I actually want. Okay, so exponential search can take this essentially infinite array of values, and it can find a particular value that you're looking for, and it does it in a logarithmic number of steps. And the reason we know this is it takes a log, because we're growing, these jumps are growing exponentially, and it's going to take a logarithmic number of steps to get a value that's higher than the one we're looking for, or higher than or equal to. And at that point, it's only a binary search between a range, and it's also going to take a logarithmic number of steps to get in there. So whatever entry number this is, if this is the millionth entry, then it takes the log of that to actually find the value that we're looking for. Okay, so this is the procedure we have, and then we want to think about how we can exploit this to actually be able to answer the question. Again, going back up here, what is the F cost that will do some number of node expansions that we want to perform in practice? Okay, and so so IBEX, as I said, is named iterative budgeted exponential search. We see the exponential search is the portion that we're doing right here, and the key actually, and this is really important. So exponential search can allow us, we can basically use an exponential search to find the next F cost. So that's what that ends up being. But we have to be careful, because if in this array right here, when I query, like I query this is basically, if it's an array, it's basically a constant time lookup that says, hey, just look up the value in that array and tell me if it's too high or too low. And I don't want to, I don't want to actually be able to have to pay anything too large when I look up a value that's too high. In particular, if I were to run an IDA star iteration with a very high F cost, I could end up doing a very large number of node expansions, and that would be just far too expensive. And so if that's far too expensive, then I would then I would pay that cost, right? I would pay a cost of doing that search, and so we'd like to limit that. And so that's where we're going to get to the budgeted portion of this. Okay. Okay, so what we're going to do is we're going to try and do exponential search, but we're going to adapt it to the heuristic search problem. Okay, and what we're going to have here is what we're going to realize is this. It's in the same way they had an array before, we can convert a heuristic search problem to an array of equivalencies. And basically, sorry, going back, what we're going to be looking at up here is building this sort of equivalency right here between the number of node expansions and the F cost. So what I'm going to have is, so this is going to be budgeted tree search, is I'm going to have a range here of values. And what we have is on the top of here, we're going to have F costs. And on the bottom, we're going to have nodes. And the idea here is, okay, I'm going to give you a budget. And what I'm going to say here, so up here we said, look, I want to do exactly 300 node expansions. So for the moment, we can think about doing that. We could think about doing that, but we can be actually a little bit more efficient here. So in particular, what I'm going to say is I'm going to have a target. My target isn't going to be a fixed branching factor, but my target is going to be a range of branching factors. So the idea here is that I'm going to have I have a budget of nodes. And this budget is actually going to be a range. So let's say I did 100 nodes in the previous iteration. I'm going to say, look, I want to grow by at least a factor of 2. So I want to do somewhere between 200 node expansions. Yeah, I mean, we can be inclusive here if we want, or exclusive. It doesn't, these are the low-level details I'm not going to get into in this lecture, but let's say I'm just going to do between 200 and 800 and node expansions. Okay. And so here what I'm going to say is, look, in this tree, I want to enforce that we get a branching factor. We want my overall branching factor to go between a factor of 2 and a factor of 8. So I did 100 in the previous iteration. Now I'm going to say in this iteration, I want to do at least 200 node expansions, and I want to do no more than 800 node expansions. And this is the key thing, because this is the upper end of my budget. What this tells me is that if I try to do an IDA star, like one iteration of a search or a depth-bounded, of a cost-bounded search, is that I'm trying to just answer the question that I was making in this previous query. In particular, is my value too high, too low, or did I find the range that I'm looking for? And the idea here is that in order to answer the same query, too high, too low, or found, well, it's very simple. If I do a search and the number of node expansions is less than 200, then my query is going to be that the F value is too low. If the number of node expansions is between 200 and 800, then I've found I have an F value that's just right. And if it's greater than 800, then I've gone too high. But the key is I don't have to do more than 800 node expansions that know that I've gone too far. So if I get to 800 node expansions, and then I can simply say, yes, whatever F cost this is, it's in the too high range, but I've limited the amount of work that I have to do to answer that question. So, okay, so try and make this concrete here. The idea here is, let's say I've done some F cost of 10 here. And the idea here is I did 100 node expansions. And so what we're going to have as a picture here is that there is going to be some range of node expansions here, that the number of nodes that are done here are going to be too few. We're going to have some range of F costs up here where the number of node expansions is going to be too high. And then we're going to have some Goldilocks zone where the number of node expansions is just right. And what's important is that this range is defined both by the number of node expansions. So in this case, 200 node expansions at the bottom of this range, 800 node expansions at the top of the range. And so what we see is the number of nodes here in this whole smaller range is less than 200. And the number of nodes in this range is going to be greater than 800. Okay. Okay, so what we have here is that now there's going to be an F cost, and the F cost just to be, we can be sort of arbitrary here, is we can say, well, maybe 27.2 is the F cost here, and 30.7 is the F cost up here. What's important, and so this is the key step here, is that this is where we get an equivalency between the exponential search. And the exponential search, what the idea here is that in the exponential search, we didn't know how many entries there were in the array with any particular value. Okay, and in the same way here, if I think about this array, I've got the number of nodes on the bottom, okay, but I don't necessarily know for the number of nodes how the F cost is going to change on the top. And so and again, going back up here, I want this mapping. Well, for 300 nodes, what's actually the F cost that gives me 300 nodes? I don't know. Because we could have ranges here where the F cost changes very, very quickly, and we could have other ranges where the F cost changes very slowly. Okay, but what's important actually is that as I increase the F cost, the number of nodes is monotonically increasing. So what I'm going to view here is that the F costs are the values that are inside, or are sort of like the indexes of the array. And then what's inside there is the number of nodes that would be expanded with that given F cost. And so what we're going to do is we're going to do an exponential search over F costs, and we're going to find out how many nodes there were for any given F cost. And then that's going to help me find the F cost that I need. Okay, I've been saying a bunch of things here, so let's just take a quick break here and let's think about what we're doing. If I knew exactly, so in practice, I know how many nodes I want to have for the tree to grow exponentially, but I don't know the F cost that it required to get that number of node expansions. So we're going to build a little algorithm down here. Budgeted tree search is going to have this as part of it, which is an exponential search that is going to say, it's going to answer the question. It's going to be an oracle that's going to answer the question, what F cost do I need to get a particular number of node expansions? In this case, let's say between 200 and 800 node expansions. So what do I do? Okay, well, so I'm going to be sampling on the top up here. I had an F cost of 10, and I did 100 node expansions. So now what am I going to do? Well, I'm going to start increasing the F cost exponentially. So I'm going to have 10, and then I'm going to search at 11. And then I'm going to increase that. Let's say I'm going to search by 13, going up by 2. And I'm going to go up by 4. I'm going to search by 17. I can go up by 8. So I'm going to search at 25. And then I'm going to go up by 16. And I'm going to search at, 16 is 41 here. So up here, I'm going to have a bound of 41. So my exponential search is basically querying at each of these points and is asking this question, is this F cost too low, too high, or is it just right? Did I find the interval that I wanted? And so for all of the F costs down here, I'm going to get a value that says these are all too low. And so I need to keep increasing. And up here, I'm going to get a value that is too high. And once I'm in this range between too low and too high, I can now do a binary search inside here. And so I'd be sitting at like 33 here, and then eventually I would come down here and I'd actually find a value that is just right. And so that's something like 29 here. Okay, so this is this process that we get, and what we know here is that the number of steps here, just like an exponential search, is it's going to take a logarithmic number of steps to get up to this upper bound that's too high, and then it's going to take a logarithmic number of steps to triangulate between the upper bound and the lower bound and get to an F cost that's actually within the range that I'm looking for here. Okay, so we know we need a logarithmic steps, and the range here, in general, this range is no larger than C star. So we know the number of steps here is bounded by the log of C star, okay? Because the search is being done within F costs. Okay, and so within a log of C star steps, I can actually find the next f cost that is going to be within the bound. Now we need to ask, how much does each of these steps cost? Because it's going to be log C star times the cost of each of these steps. Well, it ends up that the steps that happen down here at the bottom are actually all going to be less than whatever the lower bound is, but the step at the top is going to be, if I go over, is going to be equal to exactly the upper bound. And in fact, all of these steps that I do here are going to be bounded by the upper bound on my window that I have right here that I'm trying to find. That is the Goldilocks window that's just right in the middle. Okay, so I'm increasing my f cost up, 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 and then I find this f cost that's too high. I search then in between. I find the f cost that's just right. There's log number of those steps, and each of those steps costs at most the upper bound of the window. And the question is, what is the upper bound of that window? Well, in the worst case, actually, that's going to be, when I think about the step where I find the goal, that's basically going to be b to the d. Okay, the biggest, if you think about, so remember that I can cut out, I'll never do more than the upper bound right here. And so that means that somewhere inside here is actually finding the goal and the minimum nodes required to find the goal. But it's going to be between this lower bound and upper bound, and we're growing exponentially. And so what we see is that whatever this, this budget window is here, the nodes inside here are going to be b to the d nodes, approximately b to the d nodes. Okay, so I pay b to the d for each of my steps. I have at most log of c star steps, and therefore the overall running time of this algorithm is log c star times b to the d. Okay, and what's key here, again, is that we don't want to pay. So that could require me 1 billion nodes to actually search with an f cost of 41. But I can stop that as soon as I hit my upper limit. So that's really going to save me here, and it's going to allow this to work efficiently. And so now what we have here is we have an oracle. So we can think about this piece of the exponential search, that this is an oracle for the next f cost. Okay, and it's going to give me the answer in time. If C star, in this case, is not maybe the solution, but if you think about C star as being the next f cost, then what we're going to get is but the next f cost is going to be below C star, but we're going to get basically the log of the next f cost, and then the number of nodes is going to be, some b to the 1, b to the 2, b to the 3 growing exponentially. And if we were to add these up, what we'd see is that so there's going to be log basically f1, whatever the first f cost is, times b to the 0, plus log of f2 times b to the 1, plus all the way up to log f of d, if there's d steps, times b to the d. We know that all of these f's here are lower than f of d, so we can actually just factor out this log of the d, how many steps we have, and then we have that times b plus, so b to the 0 plus b to the 1 plus b squared plus b to the d, which we then know overall is equal to log. Again, what is the maximum f? Well, that's C star. And we know that this is b to the d. Okay. Okay, so let's step back a little bit. What do we have? We have an oracle for choosing the next f cost. And so let's actually write down how this works. We're going to divide BTS up into budgeted tree search into phases. Okay, the first phase is, what we're going to do is we're going to search with a conservative f cost. We're going to search with a minimum f cost that is less than the previous search, and we're actually going to use an infinite budget. And this is exactly what IDA star does at every step. We find the conservative f, and then we use an infinite budget, and we just search that out. So that's IDA star. And so what happens here is, if we're on a problem where IDA star works well, then we'll do this step, and we'll actually see that the number of nodes is growing exponentially, and then we're fine. And then if and only if, the nodes are not growing exponentially, Okay, if the nodes are not growing exponentially, then what am I going to do? Then I'm going to do this exponential search. And we're doing an exponential search on F costs. Okay, so we're going to search over different F costs. We're going to increase the F cost, and there's two stages to this. Is we're going to increase F exponentially, and now we're going to keep a constant budget. So we've bounded. Here we said you can use any number of nodes because we're using the next possible F cost. But here we're saying no, because in order to get to the next possible F cost, however many nodes, we're going to have to do that. So there's no point in putting a limit up in the IDA star step. But when we do this exponential search, then we're growing F exponentially. We really need to bound to make sure we don't do too much work. So we're going to do at most B times the previous, which is our constant, B times the previous number of node expansions. We're going to increase F exponentially. And if we hit the target, so the target number of node expansions, then we can stop the iteration, the exponential search portion. And we found the next F cost that we need to use. If we exceed the target nodes is our budget. Then what we're going to do is do a binary search. Okay, so there's the budgeted tree search has three phases. One, we search conservatively. Two, we're going to increase the F cost exponentially within a constant, and we're going to look to see if we can find a number of node expansions that are within a constant range. And then number three is if we go outside of that budget, we'll do a binary search until we actually fall within that window. Okay, and at the end of that, what do we get at the end of this? So the end of this is going to give us a next F cost. And so either we have searched conservatively, we were within the bound, we get the next F cost like we normally would with IDA star, or we've done this exponential search, we found the F value that keeps us within the budget, and when we did that search, then we managed to, in doing that search, we would also find the next F cost that we would use, and then we'd just repeat this process iteratively. Okay, so that's the general budgeted tree search process. And then what we have is the other piece upon this is the question of termination. And so there's a couple different places that we could find the goal. And so let's just think about those cases where we could find the goal, and we can show here. I'm not going to go into the full details of the proof here, but we can show here that if I find the goal, we can run some steps to ensure that I'm able to terminate. So if we find the goal in this step right here, when we're doing conservative growth here, if I find the goal, then I can immediately terminate because I know that I've exhaustively searched the previous layer, and at this point I found the goal, and I know that it's optimal because all the previous iterations have been searched exhaustively. But when I'm increasing F exponentially, I actually might skip the F cost that it actually has the goal. And so once I find a goal, the one thing I can do now is I can actually change my search. Once I find a goal, I can actually say, now there's an upper limit on how far I'm willing to search. I shouldn't ever expand nodes that are more expensive than the best goal that I found. So as I'm increasing F exponentially, I might find the goal, and I might find the goal and then complete an iteration. And if I do that, if I've completed the entire iteration, I will have also proven that there is no less expensive goal, and then I'll be able to terminate. But I might find the goal and then not even be able to finish that iteration, in which case I'm just going to remember that that's the goal that I found, and then later on I might have to do some more proof, or maybe I'll find a better goal. If I find the goal in the binary search, it's actually the same case as if I find it during the exponential search. That is, if I'm able to complete an iteration that has cost which is that is equal to the goal, then I'll have proven that there is no goal that can be less than that, and I'll be able to terminate. but it's possible I complete iterations that have less cost than the goal, and therefore I'll have to continue the search. Okay, so termination is basically, the key thing here is we must run to completion. Okay, IDA star is able to stop immediately. If we have gotten into this exponential or binary steps, then we can't stop as soon as we find the goal. We have to actually complete the iteration to be able to prove that we found the correct cost. Okay, and so just to give an example of how this works is let's look at a few steps of budgeted tree search and how it runs in practice. Okay, so what do we have here? So we're running and we have an iteration. In this particular iteration, shown in pink here, we finished the previous iteration with a cost of 13.97, and we expanded 11 nodes. So in the next iteration, we're trying to do somewhere between 22 nodes and an infinite number of nodes, and we're going to increase the F cost limit. So what happens here? Oh, sorry, let's go back and do this. Okay, so we're going to, given that, we're going to run an iteration, and what happens is we expanded 12 nodes, but we were trying to expand 22. And so that's below the iteration, and so I'm going to have to keep running this search. Okay, and now what's going to happen is I'm going to go into the exponential portion of the search. So I'm going to start growing the search exponentially. So the number of node expansions, my F limit is going to start growing exponentially. And what I'm going to do is I'm going to take my F limit and I'm going to add 2 to the power of whatever my iteration is in order to increase the F limit. So I had an F limit of 14.2. I'm going to add 2 to the 0 to that to get 15.2, and I'll run with 15.2 and see how many nodes. And because I did 11 before, I'm trying to do somewhere between 22 and 88 node expansions. So we're going to run that tree exponentially. As I said, 15.2, and as we run it, we only did 18 nodes. So we're still below the limit of 22, and so I'm now going to increase the limit again. It was too low. And now I'm going to increase it. Now, actually, from the previous iteration, we raised the F limit. We knew we have to do at least 16. I'm going to add 2 to the 1 to that, which is going to give us a limit of 18.2. So let's run that iteration. Sorry, I'm jumping these animations here. 18.2. There we go. And when I run with 18.2, we're going to count how many nodes we get here. And if we look at the number of nodes expanded, we're just going to exceed the 88 that we're allowed to do. So we're almost done with the tree. We've hit 88 nodes. We've hit our budget. So we're not allowed to continue to search any further because, as I said, there could be an arbitrarily large number of nodes here, and we don't want to pay that cost. So with 88 expansions, we stop the search. And now what we have is we have an upper limit on the F cost of the next iteration. So we're done with the exponential phase, and now we're going to go to a binary phase. We know the solution is somewhere between 16.2 and actually 18.5. So last time we were using 18.2 as a limit, but it ended up as we did the search, the maximum F cost we actually saw was 18.5. So that gives us our upper and lower bounds. And we're just going to split that difference, 17.17, and we'll see what happens. We'll see what happens when we search with that range. So we use 17.17. And now we've expanded 47 nodes. That's right in the middle of the range of nodes we want to expand. And so now we get back, use the next, if you want to increase from 11 to somewhere between 22 and 48, we're going to increase the F cost to 17.17. Okay, so it's IDA star, and then when IDA star fails, we can measure that IDA star expanded too few nodes. It wasn't growing exponentially. Then we're going to do an exponential search plus a binary search on top of that. Okay, so that gives us budgeted tree search, and I would just encourage you to look at the links at the bottom of this video. At the links, there are links to online demos where you can see these run, and so you can actually watch IDA star run, you can watch budgeted tree search run, you can watch it run over the entire tree. And we can actually see how it works better. But to give a summary of the algorithm, okay, the idea here is that we need, when IDA star fails, what's going to happen here is that the number of nodes expanded will not increase by a constant factor. And so we want this to happen. Of course, in this case, we're wanting this to happen, but we don't know the mapping between the number of nodes that would cause the tree to grow and the F costs that are associated with that. So we're going to use exponential search. Exponential search is we're going to do a exponential search on F costs using a budget of node expansions. We're going to put an upper limit on how many nodes we expand, and then we're going to do an exponential search to basically go and look at these costs to find and eventually find what is the next F cost we should use that will put us within that limit. The exponential search has a bound that each step is at most log of C star steps, and the number of node expansions is basically bounded by B times the previous iteration. And so overall, what we see when we get to the end of the tree and count up all these steps, that we're going to do a log of C star overhead, and we're going to do B to the D total nodes. And so what that gives us is an oracle that, given we give you a next number of node expansions or a range of node expansions, we're going to give you exactly the F cost that you need to get there. And therefore, we essentially have built an oracle that can tell us which F cost to use. And so what that's going to do, very importantly here, is that IDA star had a performance of B to the 2D in general, and here we're getting log C star B to the D. So this is a significant improvement in the worst case of IDA star. And it ends up that you can go to sort of any domain, like a polynomial domain or other things like that, and this approach is also going to work there. And we're basically going to turn it into an exponential growing domain. And so that's going to work out. Now, there's a few caveats. So let me just say a few caveats, and then maybe we'll look at a video comparing IDA star and budgeted tree search. So one caveat is we need to worry about what is the actual range of costs. So in the same way that A star can fail, or IDA star can fail, if we have a path of exponential length, but only a finite cost, or of infinite length, a finite cost, then that's going to break the behavior of IDA star. So there's a number of ways we can get rid of that. But the easiest way to get rid of that is just assume that there is some minimum edge cost in the world, some epsilon, that all edges must go up by at least that epsilon, and then we'll be okay in practice. The other thing that we have here is that if my actual costs grow exponentially, then if C star is growing exponentially, then we could actually get our overhead back if C star is growing really fast. So we are on domains where the cost does not grow exponentially, we'll be okay. But you could try to create instances where actually, there are no nodes except as growing C star exponentially, and therefore we might still get a very slow growth of the tree. But overall, those cases, at least for right now, are not sort of common approaches. And so this, as I said, is a significant improvement. And the important thing, really important here, is that the first step here is we're going to basically run IDA star. So if IDA star works, you'll only run this step right here. It's only when IDA star starts to fail that we try to do these other approaches. And that's why I would recommend that in general, budgeted tree search is sort of a replacement for IDA star anytime we think that we might not be getting actual exponential growth in our trees. And just to show this side by side, we can go back and show what happens if I run IDA star and budgeted tree search side by side. And so this is running on the exact same problem. And you can see the budgeted tree search is jumping down, jumping back. It's going to jump down again, but it's going to very quickly be able to increase its costs and get to the bottom of the tree. And now it's found its solution, and IDA star here is about halfway through the tree, but that's not actually halfway through the search because the search is growing very, very, very slowly. We're only getting 1 or 2 nodes at a time here, and so IDA star will take quite a long time. So this is an important improvement in search, and what it's doing here is that IDA star is re-expanding these nodes many, 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 many times because of its conservative increase of the cost it uses for search. And so the idea of budgeted tree search is that we don't have to be more conservative as long as we put a budget on the number of nodes that we're willing to expand. And that budget is basically going to be insurance for us to make sure we don't do too much work when we're trying to increase the bound really quickly. Okay, so budgeted tree search is as I said, a recent algorithm. We're still waiting for IDA star to finish here. And we'll be continuing to look, eventually we'll be looking at the graph search version of this, of BTS, which is budgeted graph search. And still waiting here, but there we have it. Okay, IDA star is finally finished. Okay, great. So we'll be continuing with more heuristic search coming up soon.